Hello everybody, welcome to Embedded on Dev. In this video we're going to explore the ELF file header in more detail. If you haven't already done so, I recommend you check out my other video, Introduction to Linux ELF Files, which will be helpful for understanding the material in this video. The goal of this video is to describe the structure of the ELF file header. First we'll look at elf.h to examine the structures and definitions that describe the file header. Next we will cross-compile a simple program so that we can examine its file header. We'll use readelf to get a readable output of the file header. We'll also examine the file header in the compiled binary, which will be in hex code. We'll use all this information to walk through each field and examine it. Alright, so the first thing we want to do is look at the elf.h file so that we can see what the structure for the file header looks like. So, just like the last video, I'm going to use the find command to find the elf.h files that are on my system. And I'll use the name, I need to put where we're starting. We're going to start from the root directory. We'll look for the name elf.h. Okay, so I'm going to use this one right here, and I'll just open it in gedit so it's easier to look at. All right, so the first thing we want to do is look for the file headers, the structure for the file header, which is right here. So you can see that there are two structures. We have here one that's a 32-bit, and then we have one here that is a 64-bit. So the program I'm going to compile is definitely going to be 32-bit. So this is the structure that we'll use right here, and we'll reference this for the rest of the video. Also, just real quick notice right here. So this first entry in this is the unsigned character array eident, and note that the eident is currently defined as 16. So this is a 16-byte character array. We'll use this right here for the rest of the video. And if you're opening this and look at it, you'll notice that down here you have all of the fields that define, all the possible values that you can use inside these fields right here. Some of them have some defined constants, and so you can find all of those down here as you scroll down. Okay. All right, so I'm just going to go ahead and close this. All right. So now what I have right here is just a simple hello world. Literally all it does is print hello world. So all we're going to do is just compile this. So I'm just going to call the ARM compiler. We'll call it hello, and hello C will be our input. Okay, so now you can see that we have it there. So I'll run file on this, and that tells us that it is a 32-bit ARM executable, which is what we want. So what we're going to do next is use readelf to dump the file header. So we'll use -h to dump the file header, and we'll call it on our binary. And so this right here is all of the data that was contained, that's inside our binary, and this is the data that is defined by the struct that we looked at earlier. So we're going to look at this in more detail throughout the rest of the video. The other thing I want to do is we're going to look at this in its binary form or hexadecimal form, and to do that I've downloaded a program called Bless, and it's just a hex editor. And so I'm just going to open the file using Bless. So it just pops it open right here so we can see the hexadecimal code for the binary itself. Okay, so this is the start of the file, offset 0, so this is in hex right here. And then I just happen to know that the 2, 3, 4, so the size of the header is 34 hex bytes. Or this right here that I've highlighted, that right there is the file header. That contains all the information that was displayed right here. So we're going to look at this further in the video, and we'll dissect it and go into more detail. So one thing that I forgot to show in the ELF file was the size of all the different data types. So we should take a look at that real quick. So from the top, you just come right down here. You notice that the ELF32 half is a 16-bit, and the 32-bit words are 30. So the ELF32 word is a 32-bit, and then the offset and the address are both 32 bits. And then this one I don't think we use, but so we use offset, we use address, we use word, and we use half. So just to make sure you familiarize with those sizes, because that affects the size of the file header. All right, so here we have the structure of the file header that I pulled out of elf.h, and the file header is defined by a standard C-style structure. Notice again that the half words are just 16 bits, and then the words, addresses, and offsets are all 32 bits. Off to the right, I have the byte offset for each section, or each field where it starts. So you got decimal here, and then you got hex right here. That's not part of the elf file, but I added it here for more understanding. So we'll reference the structure as we go through the video and examine each field. Okay, so the first field we're going to look at is the eident array. And the eident array is just a byte array that has enident number, which is currently defined as 16. So it's a 16 byte array which contains the magic number and a number of other things, including the file class, data encoding, file version, the OS ABI, the ABI version, and some padding. And we'll go into each of these in detail. So the first value we'll look at in the eident field is the magic number. So the magic number is always first 4 bytes, and it is hex 7 fox, followed by the ASCII hex for the letters ELF. So the ASCII hex is 45, 4 Charlie, and 4 6. And so here you can see the first 4 bytes in the file correspond to the magic number. And over here we have the readelf output of the program, the file header. And so you can see here that this magic number right here is those 4 right there. All right, so the next value in the ident field that we're going to look at is the EI class. This tells us the class of the file, and in most cases you're just going to have either elf class 32 or elf class 64. So in the hex code we see we got a 0, 1, and here in the readelf output you can see there's a 0, 1 for that byte, which translates to elf32, which matches what we have in the elf.h file. And the next field that we'll look at is the EI data value inside the ident field. And so this tells us primarily how it represents negative numbers and whether it's little endian or big endian. So we see here in this byte we've got 0, 1, and here in the readoff output we've got 0, 1. And so we see that corresponds with elf data 2 LSB. So 2's complement little endian, which is what's indicated by the readoff output. In case you need a review, the endian determines like the byte order of a multi-byte value is represented in memory. So for example, a 32-bit number would be represented by 4 bytes. And so with least significant byte, with little endian, the least significant byte is first in memory address. Okay, so the left side is the lower memory address, and the memory addresses get higher as it goes right. So in this case, we have the decimal value of 500, which in hex is 01 fox 4. So in 32-bit little endian, the least significant byte would be first, then it gets more significant as it goes this way. So really, it gets read backwards. So we have this number is essentially 000001 fox 4, which is what we see here, and that equals decimal 500. With big endian, it's the opposite. It's the most significant byte is in the lower or first memory address. And so again, we have 01 fox 4 for decimal 500. And so here, this is the most significant byte, and then it goes least significant as it goes. So this appears to be in human readable order, whereas little endian appears to be the opposite of human readable order. So it just so happens that this ARM binary is compiled in little endian. And we'll see that as we start analyzing a little bit more of this file header. Okay, so byte number 6 contains the version number. This specifies the elf header version number, and currently the only valid version number is 1, so generally this is what you should see. So you can see here in byte number 6 we have a 01, and that's what's coming out in the elf readelf output, and then the version says 1 or current. Okay, and so this is from elf.h telling us that there's only valid value is 1. All right, so the next byte we're going to look at, byte 7, is the OS ABI type. So this image from elf.h shows the current possible types that were listed in that particular elf file. Our program has a type 0, which corresponds with the Unix system V ABI, One thing to note is that the ARM specification states that this particular byte should be 0 unless using a type that is specific to ARM, such as 64 or 97. So here we have 64 and 97. So we would expect this to be 0 unless it was using one of these particular ABIs. Also note that not all ELF files will make use of this field. Alright, so the next byte, byte 8, is the OS ABI version. So in our example program, we have a 0 here in the hex, and then again in the readoff you can see that it says 0. And so ABI version 0 just corresponds with the Unix System V ABI. And like the ABI field, this may not be used by all ELF files. So a lot of times this may just be a 0. And the last part of the eident is padding. And so these, starting from byte 9, the remaining 7 bytes of the ident field are currently unused and they're reserved for future use. So these bytes are always padded with 0. Alright, so the next field we'll look at is the type field. So the type field starts at offset hex 10, and it's a half, so it's 2 bytes. So we see here in the hex output that it's, remember this is little endian, so it's 0002. And over here this is the elf.h file that shows us the possible legal values for the E-type. And so this corresponds with which type of binary file it is. So in the previous video I talked about executables, relocatables, shared libraries or shared objects, and then core dump files. So that's primarily what you're going to see here. So we've got relocatable, executable, shared objects, and core files, as I just said. And so we can see here we got a 2, and that is, in this thing right here, it is an ET exec. So that means it's an executable file, which we would expect because we compiled it to be an executable file. Alright, so the next field is the machine field. So this tells us the processor architecture that the binary was compiled for. This field is at offset hex 12. It's a half word, so it's 2 bytes in length. So the image shows just a few different possible values. There's like over 70 legal values for this field, so I couldn't fit it on the page, so I didn't do that. So we see here that we have a hex value of 0028, and hex 28 equals decimal 40. So what we're looking at here is ARM. So this binary, this tells us that this binary is compiled for ARM, which the readelf output confirms right here. The next field is the version field, and this value tells us the object file version. This field is at offset hex 14, as you can see, and it is a word, so it's 4 bytes. As you can see in the output from the hex file, it's 00000001, so that is just a 1 in hex, and the elf.h shows us that there's really only one valid number, which is EV current. So presumably they're reserving this for possible other versions in the future, but right now it's just EV current. And so we get version 1 in the readoff output. So the next field is the entry point address. This value tells us the address where the code execution will start. So note that this is an address in memory, not a file offset. So it corresponds to an address in RAM when the program gets loaded into memory. Once the program is loaded into memory, the control is transferred to the program at this address and it begins executing code. So we can see here that this is entry is 32 bits, so it's 4 bytes, and it's entry point virtual address, and it's at offset 18. So if we look here at the hex, we again little endian, so we got 0001 03 0 Charlie. So that right there, as we can see, the readoff output tells us the entry point starts at 1030 Charlie. Alright, so the next field is the program header offset. So this value tells us the offset into the file where the program header starts. So how many bytes into the file where the program headers can be found. Remember from the previous video that the program headers describe the segments. So right here on the right we've got segments, and so the program headers right here would describe the location and size of these segments. Okay, this field's at offset hex 1C, and it's an offset, so it's 4 bytes in length. So we can see that 00000034 corresponds, that's hex 34, which corresponds with the decimal 52. So essentially they're saying the program headers start 52 bytes into the file. And so again, the readelf output confirms what we're seeing. So it's the start of the program headers, which are the same thing, similar, also called the segment headers, and it's 52 bytes into the file. The next field is the section header offset, and section header table file offset. This is at byte 0x20, offset 32, and it is a offset, so it's 4 bytes, 32 bits, 4 bytes. So we can see here in the hex we've got 0000 1 Bravo 00. So that corresponds to, I'm sorry, I misread that. The 0000 1 Bravo Delta 0. And so 1 Bravo Delta 0 corresponds to 7,120 in decimal. So this corresponds with the start of the section headers, which are at the end of the file. So these section headers, each record in the section header table describes one of these sections right here. 7,120 bytes is where this is, and it's after all of the sections and the segments inside the file. So the next field we'll talk about is the flags field. This field contains processor-specific flags. So this field is at offset hex 24. It's a word, so it's 4 bytes in length. So if we look at the hex output, we can see we got 05000200, which is confirmed right here in the output from the readelf. This value is ANDed with various masks to determine if certain flags are set. So for ARM, there's 3 masks we'll discuss here. The first mask is the most significant byte. So this FF right here. So this is the ABI mask. So whatever number is in this first byte tells us what the ABI is. So if we look at our thing here, the flag is 0500, so 05 corresponds to the first byte. So that tells us that our ABI version is 05. And the next 2 masks that we'll talk about are the ABI float. And so what the float is how does this do floating point calculations? Some boards or some systems that you're going to be developing for will have hardware that supports floating point calculations, and some may not. And so when you compile it, you have to determine whether you want to compile it so that it supports hardware float calculations or soft float calculations. If it's soft float calculations, then it depends on the software to do the floating point calculations, which generally is slower. So it depends on what your target is. If you can, I recommend, if it has hardware for floating point, then I would recommend you do that. For this particular binary that we compiled, it compiled it for soft float because of the compiler that I chose is a soft float compiler. So right here we've got the flag, this third byte, so first, second, third byte right here determines what the float calculation is going to be. So if it's a 4, then it's a hard float calculation, and if it's a 2, then it uses soft float calculation. So those are really kind of the most important flags right here. Well, they're the only ones set in this particular ELF file. So those are the ones that I showed you. If you want more information, you can go to this source right here, which I found very useful and informative. All right, so the next field that we'll look at is the EH size. So the EH size, the EH is literally just the file header. That's what we're talking about in this entire video. It's just the file header. It's all of this information here. It's at offset 28, hex 28, and it's a half word, so it's only 2 bytes in length. So we can see here that we got 0034. Of course, 34 is a decimal 52. So that means that the size of this program header, this file header, is 52 bytes, or hex 34. So we can see that if this starts at 30, we've got 30, 31, 32, 33, 34. So this 01 right here is the very last byte of this file header. So that's all that's saying is that's the size of this header right here. So the next field is the program header size. So remember, a program header defines segments. So these are the segments right here, and these are the program headers. So this will define the size of each one of the records inside the program header table. So there will be one program header for each segment in a binary file. So this field is at offset 2A, and it's a half, so it's only 2 bytes in length. So we got 0020. So 20 hex 20 corresponds with 32 bytes. So each one of these program headers right here is 32 bytes. And we're going to cover the structure of the program headers in a different video. Okay, so the next field is the program header number. So this field just tells us the number of program headers that there are. So it's at offset hex 2 Charlie. It's a half word, so it's only 2 bytes in length. So we can see here we've got 0009, which is what corresponds with the read-off output. So what that means is there's 9 of these little program headers inside this ELF file. And again, I'll be covering segments and program headers in a separate video. So the next field is the section header entry size. So this field just tells us the size of each section header. So the section headers again are at the end of the file. So this is a section header table. And so this tells us the size of each record inside that table. It's at offset hex 2 echo, and it is a half, so it's only 2 bytes. So here we see we have a value of 0028. 28 in hex corresponds to 40 bytes. Okay, so that means that each one of these section headers is 40 bytes in length. And the next field is the section header number. So this just tells us the total number of section headers that are in the section header table. So it just tells us how many of these there are. Okay, and again, this is at offset hex 30, and this is a half, so it's only 2 bytes. So we have 001 echo, and hex 1 echo corresponds with 30. So there's 30 entries, 30 separate sections. So if you look at these, there should be 30 sections in here, 30 of these sections in here. It is possible that you can have a section header that is defined that doesn't actually have a corresponding section. So every section that exists must have a section header, but every now and then you'll get a section header that doesn't have an actual section, and it's just a special use, special case where sometimes they do that. And we'll get into that. We'll find an example of that when we go over section headers in a different video. So the next and final field is the section header string index number. So this field tells us which entry in the section header table describes the section where the strings are that contain the names of the sections. So to put it simply, it tells us where to look to find the strings for the section names. So this field is at offset hex 32, and it's a half word, so it's 2 bytes. So here we have 001 Bravo, and hex 01 Bravo corresponds with decimal 27. So section header string table index 27. So what they're saying is, right here where the section headers are, the index number 27 describes which one of these sections contains the strings to name all of the sections. So when we look here and we see all of these names for the sections, all of those are going to be inside one section, and index number 27 is going to tell us where it is. So to look a little deeper into this section header string index, here's a small portion of the output of sections from the readoff command on our example binary. So right here, this is the section header. And you can see here that the section with index 27 is the section header string table and sits at an offset of 1 alpha Charlie 4. Okay, so this is how far into the file this section where it starts. It's the offset into the file where it starts. So when we open the binary in a hex editor, bless, and we go to that offset 1 alpha Charlie 4, which is this first highlighted text right here, we see a bunch of null terminated strings. Essentially all of these strings right here correspond with the section names of all the sections that are listed here. And so when we go into more detail in the section headers and the sections themselves, then we will see how it finds which index into this table to locate the string for a given section. All right, so let's summarize what we talked about in this video. So first we described the structure of the ELF file header, and we found that inside the elf.h file. And then we examined each field of the file header by looking at the definition of the structures in the elf.h file, the output from the readoff command, and the binary file in hex using the bless hex editor. So that does it for this video. Hope you found it useful, and we'll see you again.